episode 94, titled LDA versus QDA, Choosing Discriminant Methods by Datashape, we focus on how to choose between two classic discriminant approaches by paying attention to variance patterns and the kind of decision boundary the data seems to require.
Linear discriminant analysis, abbreviated as LDA, and quadratic discriminant analysis, abbreviated as QDA, can both be effective classifiers, but they make different assumptions about how each class is distributed in feature space.
Those assumptions control how flexible the boundary can be and how stable the model remains when data is limited. At an exam level, the key is not memorizing formulas, but recognizing what shared versus class-specific covariance means and how it maps to linear versus curved boundaries. When you can read a scenario and infer whether class spreads look similar or distinct, you can usually select the right method quickly. This episode builds that intuition so your choice is grounded in data shape and sample size, rather than in guesswork.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.me in the Bare Metal Study Guide series. LDA assumes that each class has the same covariance structure, meaning the spread and correlation patterns among features are shared across classes even if the class means differ. In simple terms, the classes may be centered in different places, but they have the same general shape, orientation, and thickness in feature space. This shared covariance assumption allows LDA to pool information across classes when estimating the covariance matrix, which improves stability when data is limited. The model effectively learns one common notion of variability and then uses class means to separate classes. That shared structure is the source of LDA's strength in small to moderate samples, because covariance estimation becomes more reliable when it is based on more data. At the same time, it is also the main constraint, because if classes truly have different spreads, forcing them to share one covariance can underfit the boundary. QDA relaxes that shared covariance assumption by allowing each class to have its own covariance matrix, meaning each class can have a distinct spread, correlation pattern, and orientation. In geometric terms, QDA allows each class to have its own shape in feature space rather than forcing all classes to share one shape. This added flexibility can capture situations where one class is tightly clustered while another is more diffuse, or where correlations among features differ meaningfully by class. The cost is that you must estimate a separate covariance matrix for each class, which requires more data, especially when the number of features is large. If the class sample sizes are small, these covariance estimates can become unstable, leading to unreliable boundaries and overfitting. QDA is therefore more expressive than LDA, but that expressiveness demands more evidence. Because LDA assumes shared covariance, it produces linear decision boundaries between classes, which are boundaries that can be expressed as straight lines in 2 dimensions and hyperplanes in higher dimensions. Linear boundaries occur because the log likelihood ratio between classes becomes a linear function of the features under the shared covariance assumption. Practically, this means LDA separates classes by drawing a flat dividing surface that best distinguishes their means given a common spread. Linear boundaries can be surprisingly effective when the true separation is mostly driven by shifts in average values rather than by differences in variance structure. Linear decision surfaces also tend to be stable and easy to reason about, which is helpful when you need predictable behavior across different samples. The downside is that if the true boundary is curved due to class-specific variance, a linear boundary may misclassify regions where the class shapes overlap in a nonlinear way. QDA creates curved boundaries when variance differs across classes because the class-specific covariance terms introduce quadratic components into the discriminant functions. In 2 dimensions, this can produce ellipses, parabolas, or other curved separation patterns that bend around regions where one class has a different spread or orientation. This is valuable when the data suggests that separation is not simply a matter of shifting the mean, but depends on how variability changes with the class. For example, one class might occupy a narrow corridor while another occupies a broad cloud, and a curved boundary can wrap around the narrow region in a way a straight line cannot. The same flexibility can be dangerous when data is limited, because curved boundaries can chase noise and create an illusion of perfect separation in training. Recognizing that curvature is both power and risk is central to choosing QDA wisely. A practical rule is to choose LDA when data are limited and stability matters, because LDA's shared covariance estimate uses more pooled information and is less sensitive to sampling noise. When you have relatively few observations per class, or when the number of features is not small, estimating separate covariance matrices becomes statistically demanding. LDA reduces that demand by estimating one covariance structure, which tends to produce more stable parameters and more reliable generalization. This stability is especially valuable when you need a model that behaves consistently across cross-validation folds and does not swing wildly when retrained. LDA also fits well when you suspect the classes differ mostly in their central tendency and not in their variance structure. In many exam scenarios, the phrase limited data is effectively a nudge toward LDA, unless strong evidence suggests different class spreads.
You choose QDA when classes have distinct spreads and you have enough data to estimate those covariance differences reliably.
Distinct spreads can mean one class has higher variance on certain features, different correlations among features, or a noticeably different shape in feature space. When those differences are real and stable, QDA can capture them and produce boundaries that more accurately separate the classes.
The condition of enough data is not optional because covariance estimation is sensitive and a poor estimate can distort the entire classifier.
In high-dimensional settings, enough data grows quickly because each covariance matrix contains many parameters, and each class must support those estimates.
When the data set is large enough and the classes truly have different variance patterns, QDA's flexibility can produce measurable improvements.
The exam expects you to connect that improvement potential to the cost instability and data requirements.
Spotting covariance equality clues in scenario wording is a practical skill because exam questions often hint at variance structure without stating it formally. If a scenario describes classes as having similar spread, similar variance, or comparable dispersion, it is pointing toward the shared covariance assumption that supports LDA. If the scenario describes one class as more scattered, broader, tighter, or having different variability across features, it is suggesting class-specific covariance, which aligns with QDA. Mentions of elliptical clusters with different orientations can also hint that covariance patterns differ, because orientation reflects correlations among features. Conversely, if the narrative emphasizes simplicity, robustness, or limited samples, it often implies that assuming a shared shape is a reasonable compromise. Learning to translate these qualitative hints into covariance assumptions is exactly how you answer these questions quickly and correctly.
Avoiding QDA when sample sizes are small is one of the most important safety rules, because QDA's separate covariance estimates can become unstable and lead to overfitting. Small sample instability can show up as extreme decision boundaries that wrap tightly around training points, producing very high training accuracy that does not hold up out of sample.
This is particularly severe when the number of features is large, because covariance matrices become harder to estimate and can become ill-conditioned. Even if you regularize or constrain the covariance estimates, the basic issue remains that QDA is more parameter-hungry than LDA. In exam terms, if the scenario emphasizes few observations per class or noisy measurements, QDA is often the risky choice.
The discipline selection is to prefer LDA under scarcity, unless you have strong evidence and adequate data to support class-specific covariance estimation.
Comparisons between LDA and QDA should be made using cross-validation rather than training accuracy alone, because training accuracy can over-reward flexibility.
QDA can fit complex boundaries and may therefore appear superior in sample, even when it is simply capturing noise.
Cross-validation provides a more honest estimate of generalization by evaluating how each method performs on unseen folds. This is especially important when deciding whether the additional flexibility of QDA is justified, because the only meaningful reason to accept that complexity is improved out-of-sample performance.
When cross-validation shows similar performance, LDA is often the safer choice because it offers stability with fewer parameters.
When cross-validation shows a consistent advantage for QDA, that suggests the data truly benefits from class-specific covariance modeling.
The exam-level message is that selection should be evidence-based, not based on the best-looking training number.
Discriminant outputs can be interpreted as class likelihood separation patterns, meaning the methods estimate how likely a point is under each class distribution and then choose the class with the higher implied support.
Under their assumptions, both LDA and QDA rely on class means and covariance structures to compute discriminant scores that reflect relative plausibility.
Thinking in terms of likelihood separation helps you understand why covariance assumptions matter, because covariance controls the shape of the class density, and therefore how quickly likelihood drops as you move away from the class center.
LDA assumes all classes drop off in the same shaped way, while QDA allows each class to drop off differently.
This view also helps you communicate outputs as relative class support rather than as deterministic truth.
The model is comparing how well each class distribution explains the observation under its assumptions.
Communicating assumptions clearly is essential, because stakeholders may not care about covariance matrices, but they do care about what the model believes about class spread. LDA assumes shared spread, which you can describe as the classes having the same overall variability pattern but different centers. QDA assumes class-specific spread, which you can describe as each class having its own variability pattern and therefore requiring more data to learn reliably. This communication matters because it frames why one method is more stable and the other more flexible, and it prevents the model choice from seeming arbitrary. It also helps when explaining why performance differs across retrains, because unstable covariance estimation can cause QDA to vary more from run to run when data is limited. Clear assumption communication is part of professional governance because it ties method choice to evidence and constraints.
The anchor memory for episode 94 is that LDA shares shape, QDA customizes shape, and the trade is stability.
Shared shape means one covariance matrix, linear boundaries, and more stable estimates under limited data.
Customized shape means separate covariance matrices, curved boundaries, and potentially better fit when class spreads truly differ, but at the cost of more parameters and greater sensitivity to sample size.
The trade is stability, because flexible boundaries can overfit when evidence is thin, and covariance estimation is one of the most data-hungry parts of the model.
Keeping this anchor makes it easy to choose appropriately under exam pressure. It also helps you avoid the common mistake of assuming that more flexible automatically means better, which is only true when you can support that flexibility with sufficient data.
To conclude episode 94, titled LDA versus QDA, Choosing Discriminant Methods by Data Shape, pick a case and justify your choice based on spread and sample size.
Suppose you have two classes of network flows where both classes show similar variance patterns across features. The dataset is modest in size, and you need a stable classifier that generalizes reliably.
LDA is the justified choice because the shared covariance assumption matches the described similarity in spread, and pooling covariance estimates improve stability with limited data.
In contrast, if you have abundant labeled data and clear evidence that one class has a narrow, tightly correlated shape while the other is broad and differently oriented, QDA is justified because the class-specific covariance structure can capture that difference and produce a curved boundary that better matches the data.
The key is that you choose based on the data's shape and the availability of evidence, not based on training accuracy or preference.
When you can articulate the spread assumption and the stability trade-off, you can answer LDA versus QDA questions cleanly and correctly.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.